Today we're going to use function notation rules to do linear transformation. So we're going to start with vertical rules. That's the first page of your packet. So what we're going to start with, if you look at this table, you have all of the different rules that deal with vertical functions or vertical transformations. And our vertical rules always happen outside of the parentheses, okay? So when we're talking about function notation, there's going to be a lot of inside and outside the parentheses. So vertical is outside. We're going to start graph the following function on each graph below. This will be our starting function for all. Pause the video, graph f of x equals 2x plus 3 on the front and the back of the first page of your notes. Okay, so now 2x plus 3 is graphed on all of our graphs on that first page, front and back. So the first transformation that we have is a shift up 2 units. So we're going up 2 units. So if we look at our table, we're shifting upward k units. So if we're going up 2, our k is positive 2. So our original function was f of x, right? So now function notation says we're taking that original function f of x and we're increasing it by 2, just like our rule says here. So f of x plus k. If k is positive 2, our function notation is f of x plus 2. Applied function notation is when you take that function and replace it with the 2x plus 3. So we're going to replace f of x with 2x plus 3. And what did we do to f of x? We added 2. Whenever you're applying transformations of function notation, you need to make sure before you're done, is there anything that you can simplify together? And if we look here, we have 2 constants that we can add together to be 2x plus 5. So when we graph 2x plus 5, 1, 2, 3, 4, 5, and a slope of 2, our lines are parallel. This line just went up 2 units. Okay, so our next transformation, we are going down 5 units. So we're going downward. Look back at your table. We're shifting down k units. So f of x minus k. So if we're going down 5, we are saying we're taking the original function f of x and we're taking it down minus 5. So when we apply our function notation, what is f of x? Remember we started with 2x plus 3. And then what are we doing to it? We are going down 5. Anything that you can simplify? Here it is. So our result is 2x minus 2. So when you graph it, go ahead and graph. Pause the video if you need to.
Are they doing this at home?
So we'll see we went down 5. Because 1, 2, 3, 4, 5. So let's take a second before we go over to the next page and look at our function notation. So our function notation, remember at the beginning I said Vertical rules always happen outside the parentheses. So let's see. Was the +2 outside of the parentheses? Yes, it was. Was the -5 outside of the parentheses? Yes, it was. So now, we're going to flip back and forth a little bit here. So flip to the next page. We're reflecting over the x-axis. So before we do anything with the function notation, flip back over to look at your table. We're reflecting over the x-axis. So that's our next one down. Reflect over the x-axis. The only thing that's happening here is this negative is getting multiplied outside of the parentheses by your function. So let's go back. Negative f of x. So negative outside of the parentheses, flipping over the x-axis. And what I should see is our line flipping over that axis. So if we apply our function notation, let's take what we know, right? What is your f of x? Remember, it's 2x plus 3. And what are you doing to it? You're making the whole thing multiplied by -1. So the interesting thing about this is that that negative doesn't just apply to the slope, right? We're not just going to flip the slope. We also are applying it to the y-intercept. So when I apply that rule, negative 2x minus 3. So let's graph and see what happens. We're going down 1, 2, 3, negative 2. And you can see that reflection point right on that x-axis. So you can see that it reflected over x. Okay, vertically stretch by 3. So right here, vertically stretching something, it's like you're taking a rubber band and what you're doing is you're taking that rubber band and you're stretching it from top and bottom, right? So it's going to kind of straighten that line up quite a bit. You are literally stretching that function. So let's look. On your table, if I'm vertically stretching by a factor of a, when a is greater than 1, we're taking a and we're multiplying it by our function. So our function notation, if a, we're vertically stretching by 3, so we're got an a of 3. So our function notation is 3 times f of x, or if you just want to write it as 3f of x, right? So you're multiplying your entire function, which remember was what? 2x plus 3, and you're multiplying the whole thing, not just the slope, but the whole thing by 3. And we're starting to see a lot more here that those vertical rules are outside of the parentheses. And you see the parentheses a lot more once you apply that function notation. So if we apply that and we distribute 6x plus 9. 6x plus 9. Look at your slope. Your slope compared to the original, it's going to make that much steeper. But not only is it much steeper, my y-intercept has gone up. So we are literally stretching that line almost into a vertical form. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And our slope is 6. I can't go up 6, so we'll go down. 1, 2, 3, 4, 5, 6, 7, 8, 9. And So you see how it almost looks like you took it and you pulled it from the top and the bottom into that stretched form. So if vertically stretching is pulling it from the top and the bottom, vertically compressing something like a trash compactor, right? You're pushing it from top and bottom. So we're vertically compressing by 1/4. So our A, just like the one previously, is 1/4. If we look back at our table, the rules should be similar. Vertically compressed by a factor of A, when A is between 0 and 1. We're doing the exact same thing. We're multiplying it by our function. So my A is 1/4, and my function notation is 1/4 times f of x, or just 1/4 f of x. So let's apply our function notation. So when we apply that, remember, same thing we've been doing for all of them. What was your function? You should all be sitting at home yelling at the video. It's 2x plus 3. And the whole thing is getting multiplied by 1/4. So 1/4 times 2x is 1/2 x. 1/4 times 3 is 3/4. So compare to your slopes. You went from 2 to 1/2. So your line is going to be a lot less steep, which means you basically pushed it from the top and the bottom. So 3/4 is kind of an interesting y-intercept, so we'll just eyeball it a little bit here, but you're going up 1 and over 2, up 1 and over 2, up 1 and over 2, so far. Okay, so we can see that compression there that we've just pushed from the top to the bottom. Okay. So take a second, pause the video, and make sure that before we move on to horizontal, if you have any questions for tomorrow in class, you write them down and have them ready so that we can discuss in class. Okay, so now horizontal rules. Let's have a few conversations. So remember, vertical rules are always outside of the parentheses. Horizontal rules happen inside, so y'all know there had to be a little bit of a difference there. All of our rules are right here in this table, your two handy tables for you guys to have. And graph the following function on each graph below. This will be our starting function for all. So on all remaining graphs, you're going to pause the video and graph 3x minus 1 and then restart when you have that graph. Okay, you should have all of your lines graphed, so we can go through our horizontal shifts. Your lines are all graphed, so let's start with shifting left and right. Remember, everything horizontal happens inside your parentheses. So we're going to shift left 4 units. So when you're shifting left and right, the thing that always trips everybody up is that it seems like it's the opposite. So I'll explain in just a second. I'm shifting left H units. So let's change this to H. And we're going 4 units. 4 units to left. So my rule up here, f of x plus h. So f of x plus 4. So thinking, normally when I'm shifting left, you think of minus. You think of minus when you're shifting left. So let's apply our function notation. Let's bring our original f of x, right? So our f of x, 3, but look what's happening here. It's inside the parentheses. So what we're going to do is wherever we see x, it's now x plus 4. So that's kind of like when you're solving functions. Remember, if I said if f of 2, right, you would go back and you would say 3 times 2 minus 1. Or if I said f of x equals 2, you would go and you would say that 2 equals 3x minus 1, right? So are you replacing the entire function, or are you just replacing x? So in the horizontal case, we're just replacing x with our rule. So focus back over to your notes. Your applied function notation, we've left a part off. So 3x minus 1. So where we saw x, we replaced it with x plus 4. When we look here, we can distribute our 3. So 3x plus 12, but then we have this minus 1. And so I can simplify and get 3x plus 11. Three x plus 11, so let's graph. 1, 2, 3, 4, 5, 6, 7. So 11 is not really on there, but we'll just pretend like it is. And we're going up 3 and over 1. So up 3, right 1, which means we can go down 3. So 11. So what we've created is a set of parallel lines, right? And by shifting that y-intercept so far, it's actually bumped that line to the left the amount of units that we needed it to. So interestingly enough, even though we're adding 4, it's bumping your line to the left. So if plus 4 is left, then it makes sense for if we're subtracting, it would be right. So our next function, we're going to shift right 2 units. So let's change this to h. H equals 2. So if you're going to the right, you're subtracting your h units. So we've got our function notation, f of, remember it happens inside parentheses, x minus 2. So let's just replace the x in our function. We have 3 times x minus 2 minus 1. Distribute. And combine. And graph. So notice on both of these that your slope didn't change, right? And if you're shifting something left and right, or even up and down, our slope shouldn't change because those lines should be parallel lines. So if you look, your line went right 1, 2 units. Okay, let's flip over to the back. We're reflecting over y. So remember with reflecting over x, we multiplied everything by the negative. But remember this is inside, so somehow this is going to be flipped over this axis. Let's look at your table. If I'm reflecting over the y-axis, only the x becomes negative. So my function notation is f of negative x. So on my applied function notation, remember you have 3, now it's times negative x minus 1. So the only thing that switches here is your slope is now negative. So let's graph. Negative 3x minus 1. So my y-intercept is still the same, which makes sense if I'm just reflecting over y. But now my slope has become negative, and it's created this x. And there you can see your point of reflection. Okay, vertical stretch. You took your rubber band and you stretched it vertically. You pulled from the top and you pulled from the bottom. Horizontally stretching, we are going to pull from the sides. So if we're horizontally stretching something, we are pulling from the sides. It's going to look kind of like a vertical compression. So we're stretching by 2. Let's look back at our notes. We're stretching by 2. Okay, so first things first, this should say horizontally compress, since our factor is larger than 1. See, so if we're going to compress, it's when your factor is larger than 1. So what we're going to do is we're going to take that factor that's larger than 1, and we're going to multiply it inside our parentheses directly by that x. So f of 2 of x. So what does that look like for our function? We've got 3 times 2x minus 1. So what's the only thing that's changing here? Your slope, 6x minus 1. So let's graph. So I've horizontally compressed. We've pushed the line from the horizontal sides, which has shifted it up to look kind of like a vertical stretch. So now we've changed that one to horizontal compression. This one should be a horizontal stretch by 1/3. So look at your notes, look at your table. Stretch by a factor of b when b is between 0 and 1. So we're going to multiply that 1/3 directly by the x. So our a is 1/3. Our function notation based off of our table is f of 1/3 x. I'm literally copying these from the table and just replacing that extra variable with the value given. So let's apply our function notation. 3, and remember wherever your x is, it's going to be 1/3 of that, minus 1. Well, 1/3 times 3 is just 1. So if you want to write 1x minus 1 or just x minus 1. So your slope you have horizontally stretched, you pulled the ends of that from the sides, and it looks a lot like a vertical compression. Okay, so now take a second to reflect and write down any additional questions you have about function notation for us to discuss in class tomorrow.